Everybody, and welcome to Handmade Hero, the show where we code a complete game live on stream. I got asked a question during the pre-stream that I kind of wanted to record a very brief, very simple answer to. I know that's uncharacteristic of me. But the question was, like, what high-level languages do I find interesting? And the answer, generally speaking, is none. And I'd like to kind of explain just really quickly why, and I think a graph was the right way to explain it. Just one of these very simple, like not really a real graph, just a kind of abstract graph. But if you look at, what if we were to simplify programming languages down to just like two ratings, right? Which is like performance, let's say we put performance here, right? So this is like a high performance, right, for memory or CPU or whatever we choose. So basically, for whatever we define performance to be on a CPU scale, maybe that's not using very much memory, maybe that's being very, very fast, whatever it is that we want, but the programmer decides what their criteria for performance is. We would rate it here. And then on this axis, we would say that we want to measure like the amount of work that the programmer has to put in for the to finish the program, to actually make the program in question. And since we want to kind of make like going further out is better, let's say, what I want to do is call this like speed of development, right? So this is basically like over here is like fast, and here is slow. Okay? And so if you look at something like assembly language is like here, right? So I can do anything. I can make the best program, but it takes an incredibly long time for a number of reasons. One is that I have to manually code lots of stuff that arguably maybe a computer could have been doing for me, including things like instruction scheduling, register allocation, things like this. So, it takes a very, very long time to program it, but anything the CPU could do, anything, the most theoretically best possible performance for any situation, I can get it. Because there's nothing a computer can do that I can't do, right? 100%. So what you end up with is high-level languages. C is maybe like I don't really know where to put it, but maybe like here, let's say. I'm not really sure exactly where it goes, but C is like here somewhere. High-level languages, all the ones I've ever really seen, they're all like over here somewhere, or over here. Some of them are here, which is ridiculous. But they're basically like in this band. And so there's kind of this quadrant like up here that there's nothing. There's nothing that's like I can do the best possible thing and be very fast. Now, it's worth noting that what I'm talking about here is for the same program. So it doesn't count to say, let's say you can write inline assembler in your C program. That doesn't put it up here, right? Because as soon as I have to write inline assembler, I'm back to this slow, right? I've moved backwards, so I would go back to here. So, for example, if you take a language, your language is, Rust or something like this, if it's only actually as good as C, meaning it only really produces the same speed win in terms of development as C when you're writing code that's as fast as C, then it's only like here. And if it added a little bit to that, then maybe, it can go to like here or something or there or whatever, right? But I want to see this language, right? I want to see the language that allows me to construct ASM programs exactly the way that I think they should be constructed, but in a fraction of the time that it would have taken me, right? And I actually think this is achievable. I don't think this is a pipe dream. I think what happens is no one tries. Like, nobody tries to do this. They sit down. Oftentimes, the people who make languages don't even know this. They're like people from a university who don't actually program in assembly language very often, right? If at all. They aren't really sure what the maximum performance is for most things on their computer. And only like somewhere down the road, if their language becomes popular, does it get a back end with an optimizer and stuff. And then some people are working on it who care about this, but it's too late at that point because no one was thinking about the design of the language, right? In terms of those performance. So most of the time, they're not even thinking about this. And, you know, you're just not getting people who actually try. I think with multi-threading, this becomes even more important, right? Because now we're talking about wanting to have language features that allow me to write like things very easily that can be distributed to lots of threads in the optimal way and stuff like that. Again, really, really important for someone to understand what the optimal multi-threading code looks like for a lot of situations before they can even think about designing that language. It can't be an afterthought. You can't add multi-threading as a secondary step to your language. That's totally not going to work, right? So I think that this is the problem, and this is why I don't tend to like any new high-level languages, is because they always ask me to go further down to get further out. And I don't want to go down. I want to remain here, and I want to move this way. And if I ever saw a high-level language that actually allowed me to move laterally, I would probably start using that language. But it would have to be reasonably far, because like if I'm only going to get a little bit further, it's not going to be worth the effort to switch over, right? So what you want is a big lateral movement this way, and you're probably not going to get all the way to here because that's like the perfect language or something, right? The fastest and best or whatever. But, you know, I think we can get a lot further into this quadrant than we have before. So that's my feeling about high-level languages. Even the name sounds dumb to me. I think as soon as you call it a high-level language, you're sort of admitting defeat to begin with. I think what you want is a high-productivity, low-level language. If you want good software. If you're just interested in sitting around and collecting your Series A funding or whatever it is, do whatever you want. Doesn't matter, right? There's way more software existing in the world right now than there are good programmers. So it's like, you know, it's the type of world where you can, at least at the moment, it's pretty easy to get by on not even mediocrity, just like poor. I don't even know. It's easy to get by without much. And what place on this graph is JAI? I don't know. I've never used it. It's also not done yet. I mean, they're still working on it. I don't know. But, you know, once it's ready, I think it'll probably be pretty favorable on that graph. I don't know it's going to get quite as far to the other side because JAI is still more, I think, about producing a language John likes to program in than it is as a focus on performance kind of language. But in terms of high-level languages, it's definitely got more performance sensibilities than a lot of languages that I've seen. So I think that bodes well for it. But, you know, like I said, I've never used it, so I have no idea. All right. So let's get started. That was just that you know, that's just. Oh, where is this one on that graph? Lisp is kind of over in the other. It's pretty down low. Lisp is extremely bad at performance. The reason I said Lisp was interesting in the pre-stream was just because for a very early language, it had a lot of good ideas. It was like, oh, okay, how can we make things very flexible so that the programmer can produce code directly as part of the program, which allows a lot of powerful meta-programming things to occur. And unfortunately, not a lot of languages picked up on that who weren't similarly kind of non-performant interpreted. But you can do a lot of things with stuff like that if you just like restrict them maybe to compile time, or if you ship with a JIT. I think those things are important, right? All right, so let's get started. Let's do it. I've been watching, there's a a show on YouTube. Well, I guess I don't know what the show is called, but the channel is called, because I don't know if the show has a name, but the channel is called Guga Foods. I think it's Gugafoods. And I think it's this guy. I think he's Brazilian, and he does like all these like really good like meat tests. Like he's got all these like steaks, and every show he'll like do something interesting with the steaks as a test. So like one example was he took like 4 steaks and he packed them in various like packings that people had said were good for tenderizing steaks, like pineapple, or just like salt, like different kinds of things that people had said. And then he, did it, tested them, grilled them each, and then he tests the flavor, right? And it's a pretty cool, if you like beef, if you like meat things, which I do, it's a pretty cool show. You'll enjoy it. You should go check it out. But he has this really cool, his voice, and I don't really, some of it's accent, but I think most of it's just him. He just has an interesting voice. And so every time, right when he's about to like do whatever the money shot is, like he's about to do the fire up the grill and like put the super steaks on, which you're super looking forward to because they're all like always beautiful. He goes, "Let's do it." He just has this really funny way of saying it, and it totally sticks in my head. You'll see when you see he has a really good voice for shows. I don't really, but because it's not very distinctive. But he does, and it sounds cool. You'll see. You'll end up appreciating it. It's just a good show. He has like, I don't know if it's like his nephew or if they're related or something. I haven't gone back and watched like the original introduction ones, so I don't actually know. But he always has this other guy there with him, at least one other guy. His name's Angel, and he doesn't tell him like what they're doing, right? And so like he's always very like, okay, he's prepared this crazy test, and then he's like, okay, Angel, like let's test it out, and like it's good. You just go check it out. Watch the show. If you like beef at all, watch the show. I don't know if they've ever done anything besides beef. I think they do sometimes. It's just mostly they do beef. And I think because they're very popular now, it's not like some weird small show I found. It's a very popular show. I think they get like sponsors to send them beef now, so they get all kinds of crazy beef. I think, maybe not. I don't know if they actually pay for it themselves. Some of the beef's very expensive, but I guess, hey, if you got a popular YouTube show, you're probably making reasonable ad revenue. Anyway, all that aside, let's get started. We sort of took the first steps last Saturday. I was planning to be able to program Sunday, but I got sick. I'm still a little bit sick, but I'm mostly recovered now. My voice is not worn out, so I can do the show. I wasn't like so sick I couldn't do the show or something in terms of like physically. It was just my throat was so aggravated that I couldn't talk. I was still fine. I could walk around. I wasn't really sick in that sense. I couldn't really. I wouldn't have been able to do 2 hours of talking. I would have been like. But anyway, so what we didn't get to do on Sunday was sort of get started on the implementation of what we had discussed doing on Saturday. And what that is moving our system over to just use light probes because I finally realized after reading a paper, I haven't actually read the whole paper because I wasn't even looking at that sort of stuff, but I just wanted to see what the answer was to something that I thought you couldn't do, and it turns out that like basically everyone already does this thing, and it's actually a pretty easy answer, which was just how you propagate light with light probes if you don't have an offline solution. And I didn't realize it was as simple as it was. I should have thought of it, felt kind of stupid. If you're missing why I was stupid, I discussed it on Saturday stream, so go take a look. But anyway, so we're pretty much not really changing very much about our lighting algorithm at all. We're using the exact same thing that we were using. For all intents and purposes, we're going to modify it fairly mildly today or over the next couple weekends. But the big thing that I had wanted to always do, if I could have done, but didn't think I could, was reduce where we're sampling from. And that's what light probes are. I couldn't think of a way to do that exactly because I didn't realize you could just sample them at runtime during the propagation phase. I don't know why that never occurred to me. It just didn't. So anyway, that's all we're doing. And it's going to take us a little while to do it. But because, you know, lighting is complicated, I always say it's one of the hardest things you can do in graphics. So it's going to take a while, but there's nothing magic here. You've already seen me make the whole lighting system. It works pretty well. We're just talking about making it more efficient. And so switching to light probes, one of the things I was starting to do here, and I think we actually, well, actually I know where it is. It's down here. So, but I think we got started on it, and then I said, well, we're going to save it for tomorrow. In fact, here it is. So this build spatial partition for lighting function, and you can see that's doing the lighting solution here. Basically what we want to do is, oh, sorry. I take it back. We already had that. Oh, yeah, that's right. We already had one in there. Never mind. That's not the one I wanted to talk about. That one is actually the one that we're using during the raycasting, which we may also want to update here. But I thought we added one for voxelizing. Did we not? I thought that's one thing we added in here that I started before we ended. No? Because that's not it, right? What happened here? Huh. Yeah, here's our light probe spatial index. Didn't we have this? Here it is. All right, we did. I just, for some reason, am blind and can't see it. Anyway, so on Saturday, we started with this function. And this is basically just saying, look, I want to be able to add these things to a spatial index. And the reason that I want to add them to a spatial index is because I need the lookup to be fast. I don't probably want to go, before we had sort of a, like a, I want to call it a light cut system. That's usually what they call it in the literature, where you have like one large lighting thing that encompasses your entire scene, and then it breaks into smaller ones, breaks into smaller ones, breaks into smaller ones. So when you're raycasting, you just say, depending on how far out I am, as I leave the immediate region that I'm in, I'm going to look at like less and less detail how the scene is described, right? And that's the kind of thing that I'm not sure if we're really going to want to do anymore. We're probably going to leave it in at first because it's already there. We're not going to like pull it out preemptively. But we might not really want it anymore. However, you may ask the question, well, why don't you just use that? It is a spatial partition. It is, but we're going to need a very, very fast spatial partition for looking up the light probe contributions to any individual hit. And the reason for that is we're going to have to do a lot of those evaluations. And again, I really think we want to do it in something like a voxel. Again, I'm not 100% certain we don't want to use a multi-resolution structure for this, but I'm pretty sure what we want to do going forwards is to just use regular raycasting, no level of detail, because we're going to count on the light probes to move stuff around for us, and probably not really use the hierarchical stuff anymore. So, you know, the hierarchical stuff we maybe use for hit detection, but you know, we're going to stay away from that probably for actually doing the lighting sampling, because I think we can probably get away now with just doing direct lighting sampling everywhere. Don't know. As I'm saying it, I'm sort of having second thoughts. I'm like, maybe we should be using a hierarchy for that. And it's hard to say, because if you think about what happens there, you know, that hierarchy that you build, we could just have it always be a light probe hierarchy, meaning we take all of our lighting probes, we merge them together, and so when you raycast something, as you get further out, you just use that composite light probe. I don't know. It doesn't thrill me, so I think I'm going to try and say let's stay away from that, and we'll just concentrate on, when we do our spatial hierarchy, we're just going to do a we're just going to use that for accelerating our hit detection, and we're not really going to do anything else with it. That's probably what I'll stick with. Okay, so moving on, as we do add probe to spatial index here, we sort of sketched out what this routine would look like. As you can see, we need some kind of a function that will take the spatial index in question, and it will take a position, like something that says, here is where, some 3D position in space. And from that, we want to get back something that is in our spatial index, right? Because the spatial index is basically a big voxel that we're laying over the scene, and we want to map things into that voxel. When we loop through all of the voxel points, we will then insert this probe in there if this is the best probe. And what you can see here, we're not actually using any kind of tests. We need to use some kind of test here. But what's happening is saying, look, let's get whatever light is in this spatial index at the moment. When we get what light is in this particular portion of the spatial index, what we want to do is we want to figure out whether or not we should replace it with a new one that's getting inserted, right? That's what we're trying to do here. That way, each cell of our voxel will always have some lookup into a light probe that's supposed to be used there. Now remember, these things will need to be sampled all together. So when we actually go to do a sample, we need to find like the ones that are at the corners, and it's a little bit tricky. I mentioned this at the end of the stream. I'm going to mention it again because it's something that we're going to have to grapple with. It's probably the most interesting bookkeeping element of this scheme. But what happens with our voxel is if you look at any given voxel cell, we're going to have a fundamental problem where, all right, here's our axes, y, x, z. If we always just consider the minimum corner primal, so this is our minimum corner. So we know very, very easily with a very simple multiply and truncation, we can index into our voxel in like basically 2 ops, right? Pretty straightforward. We may need a clamp in there, but so 4 ops tops if we clamp there. If we actually just make sure we only ever allow inbounds values by sizing the voxel appropriately, then you only have 2. So either 2 or 4, either way, very, very cheap, right? So in here, when we get this particular index back, we can then look up something, right? This value is going to give us something in our light probe set, right? Or I should say group. So in our light probe group, we'll have data, but the question is just what data? Now, in a perfect world, we would just have a light probe, and you would just use it, and so right here would just be the probe, right? And that'd be the most efficient thing. I look up in the voxel, I get the probe, I light with the probe. So why can't I just do that? Well, the answer is because at some point, there's another probe, right? So at some point down the voxel, as I keep going this way, at some point, I'm going to get another probe. There's a probe here, right, that gives me good answers for things inside this cell. And there's a probe over here. At some point, you should be lighting with this probe, not this one, right? And if all I did was for every voxel, I just picked the closest light probe and used that, then we would see somewhere in here, when that answer changed, you would see a lighting pop. So as my object would move through the voxel and across the voxel boundary into the next voxel where the answer changed, and it might not change here, like maybe it's the same here, so the pop wouldn't be here, and it's over here that the pop is, right? Who knows? But some number of voxel cells later, as I pass into one that has a different closest light, I'll see that lighting pop. So what I need to be able to do here is I need to be able to provide a set of light probes, like some number of light probes that I can use together to blend, right? And as I'm saying it, I'm realizing that actually it's simpler than I think it is, because there's no penalty for having two voxel cells next to each other have the same light probe, actually. Okay, so what we could do instead is just discretize... okay. I think we have the answer here, as I'm saying it. So here's what I think we do. Let's just tell ourselves that the requirement for our voxels is that the voxels themselves will be aligned with the world such that the light probes are always considered to be... Okay, so the only thing I'm worried about is if I ever want to have a moving light probe. So let me just say this first, and then we can talk about that case in a second. If we just assume that we'll place our voxel grid reasonably, and for any given voxel cell, we will just say that there is only one light probe, and that light probe is considered to be in the middle of the voxel cell, right? Then all we would have to do is just assign every voxel a light probe, and even if two voxel cells next to each other had the same light probe, that'd be fine, right? And then when we go to gather, you just use the 8 voxel cells. Whatever their 8 answers are is what you use, right? And that's it. You just blend between those and you're done. And that's great. The only thing that doesn't really work well for is if light probes move around. Because if light probes move around, then the approximation that they're just in the center of the voxel cell doesn't really work, right? Because as they move, and right, when we look up the light probe, we can get its actual position. So it's not a storage problem. We know where the light probe actually was. But the problem is we can't really use that, because if we used where the light probe actually was, we would again get discontinuity as we move across the boundary. If this light probe is right here, and then the next voxel cell over, there was a light probe that was close, ends up being closer, then as you move between these, unfortunately you would, well, I guess the more answer is, let's say it was really close to that boundary. As I move through here, inside this voxel, right, I'm still using this, and I'm not really vocalizing this properly. I think this is an actual problem, but every time I try to vocalize, I'm like, well, that's not really technically a problem. Let me use a 2D example. See if I can work it out. So here are the points at which we store which light probe is closest, right? So what I'm worried about in terms of light probes moving is, suppose I have an entity and the entity is taking a path, right, however it wants to, through my voxels. You know what I'm saying? And maybe that's a little bit too regular, that path, so maybe it's this kind of a thing. So I have an entity that's moving through these. And what I want to guarantee is that at no point, so these are all the places where the equation changes. As it crosses that voxel boundary, right, my equation will change. Now, how will the equation change, right? The equation will change because the light probes under consideration change. If we take only the 2D problem, then while you're inside this region, right, these are the light probes. These they're not necessarily light probes, they're indexes light probes. These are the indexes into the light probe array that you would be using. And we don't know what they are, but we know there's 4 of them, right? So you're using light probes A, B, C, and D, which might all be the same. They might all be A, right? It might be there's only one light probe in this whole region, so it's all using A, or they may all be different, maybe A, B, C, and D, right? But while you're in here, this is what you're using. Now, when I cross this boundary here, I change, right? If this is A, B, C, D, then C and D remain in the active set, but A and B go away, and whatever the answers here would be, E and F, that's what I'm going to use now. So I've moved from using a window that looked like this to using a window that looked like this, right? So it used to be that, it's now that. And so what must be true in order for this to be, to not see a lighting discontinuity, like a change in lighting that's perceivable as a pop by the player every time they move across that boundary or anytime a monster moves across that boundary, right? If you look at what will happen here, we're going to be blending these together, so that means there are weights, right? There's a W0, W1, W2, W3, right? There are weights multiplying these lighting contributions. What that means is by the time I get to this barrier here, these had better go to 0. If I just pretend that the contribution of this lighting source is sort of effectively, you know, or if I just assume it's like right there or whatever I want to assume, it's like a diamond or something, I don't know, whatever I want to assume. If I want to assume that it goes to 0 as I hit this boundary, these two, this and this, if I want to assume it goes to 0 as I hit this boundary, that effectively treats its contribution as if it were in the center. Now, that doesn't mean that we have to use our computation of how the lighting gets placed on the entity doesn't necessarily have to use that position, but it does have to use those weights. Because as you move closer to this cell, you must get rid of your contribution from here or you'll see the pop, right? So, same with these. On this line, when I first cross over, the weights on this and this, those had better be none, right? Because I can't suddenly get a contribution of that lighting. So all I'm trying to say is that there's a trilinear blend, bilinear in the case of the 2D example, but trilinear when it's actually a voxel, that has to control the light probe contribution for any voxel cell. What that means is that when a light probe itself is on the move, so if I was to move a light probe around, then we effectively have this issue where as it crosses the boundary, we would produce a discontinuous lighting change. Because when, I think anyway, when it's here and it crosses over into here, that change in which cell it's in will change which contributions it gets, which would have to itself have been done smoothly, right? So that would mean that when we are actually talking about these particular, like these actual lights, as they move through the voxel boundary, we would have a problem, and we would have to effectively be smearing them out so that their position also was getting blended. And that just, again, starts to get just a little too complicated, right? So what I'm wondering is, I'm wondering if that just means that, you know, for our purposes, the simplest thing to do is just say light probes don't move. They're fixed in the world, and you just use them as if they were at the center of the voxels that you're in terms of blending, and off you go. It's a solution. It has some drawbacks. But compared to the other options, I'm really not sure how to... I'm really not sure how to do anything else. Because if you think about how we want to structure our lighting at the lower level, we definitely want a fixed algorithm for sampling, I think. I don't think we want to go down the route of having our pixel shaders doing ridiculous crap like, you know, like going and looking up into spatial hierarchies and stuff like this. I just don't think we want to go that route. We want something where we know we do a fixed set of operations that produce a fixed set of lights that we then use, right? A nice, clean, like, fetch and things, do and ops, done, right? And so that just puts you into voxel territory. There's not much you can do about it. And once you're in voxel territory, I think you're kind of stuck with having things make their contributions based on their arrangement in the voxels, which means we kind of just want to place light probes at the centers of voxels and be done with it. I think that's fine though, because again, what we're trying to do here is have a nice, soft ambient lighting to the world, right? We're not doing hard shadows. We're not doing any kind of like harsh. It's supposed to be soft, warm, like a pleasant glow to it. You know, it's Christmas time, you know, and Krampus is out. So that's, I think, okay. And so I think what we would want to do is say the voxel is like fixed in world space in terms of its alignment. And we will just take our light probes and consider them to be inside, at the center of those voxels. I think that would be okay. I think. And what we can probably do is we can probably make it so that we also, because we know we're placing those light probes, we can probably also do some work with making sure that nothing is too wonky there. I think this will work out. So I'm gonna give that a try. It's a lot. It's a lot better, I think, than what I was gonna do there. I think that's the right answer. So I'm going to go ahead and move forward with this, and I'm going to just do I'm going to make it even more straightforward than we were going to originally. I'm going to make it pretty simplistic, actually, which is nice, because the simpler the better with something like this that has to run at runtime. It's not an offline light process. So anyway, in our add probe to spatial index, I still want to retain this part because we still may want to flood fill regions for lighting, so that places that don't have actual light probes placed in them can just use nearby lighting and still work. I think that's good. So we want to maintain the flood fill. But we're just going to say, look, there's just one light index per voxel. That's all we're going to do. We're just going to go from there. So when we need to actually place something in the light into the system, we would say here, you can see us asking for the existing index, getting that light probe out. And if we get a light probe out, well, actually, in this case, we have to. You look at what happens with get probe here. There has to be something there, because existing index would have been 0 if there wasn't. So actually this... Well, you know, I probably wrote that because I was going to do this, maybe. So what we want to do here is say, look, if the centroid of the voxel, if it's closer to us than it is to the probe that's already in there, we'll fill it. If it's not, we won't, right? So we're pretty much going to want to do, like, distance to us and distance to existing, like that. And then what we want to do is compare those. And in this case, because it's a comparison, we don't need to do a square root here, because the squared version, which we'll get when we do the distance squared, which again would, you know, avoids use of square root for no reason. It's just extra ops we don't need. We can just compare the squares. If the squares compare one way, the square roots will compare the same way, because we know they can't be negative. All right. So in this case, we can say, look, if the distance to the existing is greater than the distance to us, then we will replace what's in there with us. Otherwise, what's there stays. So all we really need to do now is figure out how to actually compute these two. And obviously a light probe in this case, which we haven't actually stored in any particular way, you can see we don't have them yet. But a light probe, once we make it, should have this information. Meaning a light probe should obviously have in it a p-value that says where the light probe was, right? And then it's got some other stuff, and we don't really know what that stuff is yet. But it's got some other things, probably like a color value, right? And that color value would be for maybe the 6 faces of a cube, because we assume it's going to have like a, some kind of lighting. If you wanted to go kind of down more theoretical paths, you could consider using some of the other ways of storing lighting information. There's spherical harmonics and things like this. We're probably not going to go down that route because I haven't played much with those kind of lighting representations, and I'm not sure how good they really are. And so before I would start teaching you some of those, I would want to experiment them a little bit myself and decide on the math whether I think they're worth it or whether I think they're just kind of one of those fool's errands. So we're not going to do that, but we'll do some kind of encoding of a directional light here. And so maybe we'll say we've got, a cube mappy style lookup. So, maybe we've got something that looks kind of like that, which is we have 6 directional colors in there. And those are the light contributions that we have from each of our 6 directions. And that would be our light probe, right? So it's a pretty straightforward system. It's basically just 7 V3s, and that's all there is. It's a little unaligny. It would be nice if there were 8 V3s, but I'm not sure what the last one would be. I mean, one thing we could do is keep track of the exact light direction. But I don't know that we really want to complicate things that way. It doesn't seem like it makes much sense to do so. Yeah, I can't think of any real reason to do that. So I think we would we would probably just do something like that. I don't know, there's other ways we could approach it, but again, it's a little unaligny, but it's okay, right? So there's our light probe. If we got one of those out, like in this case here, then it should be fairly straightforward to go from there. At the outset of this, we can get the one that we're talking about here. So this probe, and maybe I'll call that distance to this. If I was to just do the exact same call for the one that we got out of the system itself, out of the spatial index, if I just do that real quickly and get the probe that we're asked to use here, then what I can do is this equation would be the same. So I would just say, well, okay, I know the distance to this probe is this probe. Maybe this is existing probe. So in both cases, I know the location. So all I need to do is just take the length squared of the vector between the place I want to measure for closeness and the position of the probes. That closeness position is the centroid, right? So this is the voxel, or I should say the cell center, right? And so when I'm in here, I need to be able to come up with the cell center for a particular set of voxel coordinates, right? And so this right here, this V3U is our cell coordinates, right? And so I want to be able to ask for this spatial index and these coordinates, what's the cell center, right? When that comes back, then I can go ahead and, with my get corner light index here, I can pass the same coordinates down, and then I can just finish up the work here by, taking the length squared with that center. So this would fill out the spatial index with exactly what I wanted, which is great. And then when it comes to lighting time, what I want to do here is say something like, get lighting 4 or something like this. And when we pass in the spatial index, and presumably we would do two versions of this, maybe something like that. We're going to have like a cell position and then a world position, and these get sort of translated, right? So in here, we would want some way of saying map, well, we have it right here. Map into grid. And then we can just sort of thunk through. So we can call it with a real position. And if we do, what we'll do is convert it to a grid position and then call this. And then when we do this operation, what we need to do is from the cell position, we need to be able to get effectively each of the 8 surrounding probe values, and we are going to blend between those, right? So what we want is 8 probes. And when I said 8, of course, I mean 0 through 7, right? So I need to get 8 probes, and then I need to blend their results together. And I guess I'm not sure what the most efficient way to do that would be, but I think the answer is that you actually just want to produce the blended probe, because that's probably less work than doing the lighting for each probe and then blending the result. I would think. But I don't know. It's hard to say, right? Because there's 2 ways we could do this. One is that you light with all 8 probes, and then you blend the results. The other is you blend the probes, and then light with just one, with just that composite result. I'll be honest, I really don't know if I can tell the difference between those two. We may have to analyze that a little bit carefully, but just, you know, trying to blind guess, I'm not sure. It would depend a lot on what the lighting equation we were going to compute actually was. In this case, this is during light propagation time, this would be called. And during light propagation time, as you might expect, light propagation time is strictly propagating like a diffuse lighting, effectively. And so we wouldn't really be computing much of a lighting equation. It would just be a cosine fall-off kind of a thing, probably. Not really much else. And so it's possible that it would just be quicker to do the light computation on each probe first and then blend the results. It's possible. I'm not really sure. However, what I will say is that it brings up something that we need to be able to do here that we're not doing as well, which is this needs to have a UVW come back that is the lerp values that we would get to blend these things together. Because, as you might imagine, in order to blend between them, we would need to know not just the coordinates of the particular cell in the voxel, but where you were inside that cell normalized out. So the UVW would need to come in here as well. So during this map into grid here, we would need to also get that residual value. And so this here would need to be computed, and it probably wants to be computed as part of this, right? So I'm guessing that it would be something sort of, this map into grid would probably be something we'll have to write out that returns both of them, but we'll see what happens in a second. So when we do get probe lighting 4 here, this is what we're going to want. When we want to get our lighting probes out, not particularly hard to do. I think we just say get probe by, or get probe from cell or something like that. And we just say like cell P, right? And for some reason, the lighting solution is not getting passed here, but it needs to be. There we go. So in order to look up the probes here, we need to get this multiple times, right? Oops. So what we're going to do here is walk all ways we can, right? So, I mean, I could write it out completely longhand here too, to just say like this is the, the one where we don't offset it at all. Here's the one where we just offset 1. Here's another. Here's another. Here's another. Oops, I forgot one. There it is. And so these are all of our different possible light positions, right? Positions in the voxel, each of the different vertices of the cube, right? So I've got them all here. And so then if I want to blend them together, like I said, I'm not really sure which way we want to do this, but you can imagine something where I would say like, okay, yeah, let's just blend the probes together first, maybe. So here's our composite probe. And what I want to do is for each color, right, all 6 of the faces of that cube, I want to blend all 6 together using this UVW as the determiner. So what I want to do is like I want to like do a thing where we sum light probes in here. So like an accumulate or like accumulate probe, something like that. So I'd say, all right, this is the probe we're accumulating into. I want to accumulate P0 in there. And I want to have some way of talking about the weights that I want to use to sum it, right? And so the thing that we're going to get here is we've got 3 weights, and each weight should affect each of the corners differently. So for example, if you look at the UVW X, Y, and Z here, well, as those go up, I am moving away from the minimum corner. So because this is 0, 0, 0, the weighting here is going to be like this. If all 3 were 0, that's the maximum, right, that I could have. And by the way, there's no sense in passing all of these because we know that it's just going to multiply them together. So that's what my actual weighting is going to end up being, right? As I move along any of those 3 axes, I fall off to 0 as I get to the end of that axis, right? So this is basically what we're looking at, and we just know we're going to do a bunch of these, right? I'm going to accumulate each of these in here, and as I accumulate each of these in here, I'm going to change based on this, right? I'm going to change which one of these, which of the UVWs are negated and which aren't. So in this case, this is the one that's on the far end of the x-axis. That means that I don't want to negate the UVW of x, the x component, right? We come down to the next one, and the same is true of y, right? So this probe was on the maximum end of the y-axis, so we want to stop negating that one. This one's on the maximum end of the z-axis, so we want to stop negating that one. This one was on the maximum of both the y and the z axes, And then, oh, that's the opposite. There we go. And this one. And then finally, this one. All right. Now this last one is not the maximum of all of them. So it doesn't get any of these. Okay. So I think that looks about right. Those match up nicely. This accumulates those into our probe. And off we go, right? Now, it's a little bit wasteful because technically the first one, you don't need to accumulate. You could just set it directly. It would save us the trouble of setting this to 0, but maybe we'll get lucky and the optimizer will help us. Who knows? At the end of that accumulation, we have a single light probe. And we can now actually get the probe lighting back, right? We can figure out what the light probe looks like that we actually need to light against. And what I'm going to do here is I'm going to say maybe we actually just we send back what the lighting probe was. That's just how we'll do it right now. Hopefully this will help. We'll see. So I think we're going to do it like this. This allows us to get whatever the composite light would be at this location. And so once we actually do that accumulation, we now know what that light is, and we can return it. Right? And so that's actually, I'm going to call that result now because that's what that actually is. Oops. And then we're good to go. So once we have all that, really this map into grid part of things is a bit of a problem here. So we're going to need to write that, and we're going to need to make sure we can get our UVWs from it, but we're also going to need one other thing here, which is that once we have one of these, we need some way of computing the actual lighting from, like a normal, right? So if you imagine now we want to do like get light, get incoming light, something like that. If we have, or light with probe, something like this. So in here, if we say, look, give us a probe and give us a excuse me, position in a normal, we're supposed to be able to return the light. Now, we don't really need the position anymore because once we have the light probe, we've already assumed that the position that we were taking has been blended with the lighting, has been blended with the probes that neighbor it to produce a single probe that's accurate for that point. And so once we do that, we don't really need to take into account the position, I don't think, anymore. So we just need the normal, and what the normal is going to do is tell us of these 6 faces, which ones are going to be combined to produce the actual value of the light, right? So that's what we need to do here. Now, the normal itself kind of tells us the answer in a way, but not exactly. What we need to do now is have some kind of a function that takes colors that are sampled for particular directions and produces a smooth blend between them, right? And this is not as easy as it maybe sounds because these values don't interpolate kind of cleanly, if you will. Let me try to give you a little bit of a perspective on what I mean by that. I know it's a little bit confusing. Never put our day marker here. So if you take a look at what's actually happening here, let's just take a cross-section of what happens with the normal. and pretend we have a few lighting values of the kind I'm talking about. And you can maybe see what I mean by we have sort of an issue here. So if I have a direction, and what I'm saying fundamentally with something like a cube lighting map like this is I'm storing like a color at each thing. So maybe there's a color off in this direction, so this is color Y, right? And there's a color off in this direction, so this is color X. And I want to know what's the color incoming at N if I assume that I want to smoothly blend between these two incoming light values. And color is probably the wrong way to say it. It's a light value. It can be whatever we want, right? But point being, whatever we're storing for our irradiance here, or I guess it's incoming light, so I don't know what you would measure that exactly in, but let's see. See if I can use the right term. Yeah, so I think we want irradiance, right? It's the radiant flux received by a surface per unit area. So even if we were trying to make a physically accurate thing, and so we have like an actual physical light incoming value here or here, no matter what it is or how accurate it is, we still have the same problem of we're only storing it at a fixed set of sample points. And we need to produce a smooth blend between them for our lighting. So we need to know for a particular normal what is the correct contribution between this and this. Now we know that the normal itself is represented as nx and y, and of course there's an nz, but we're not talking about that right now because we're just doing the 2D slice. But for the nx and y, it would be nice if we could just do something like, well, how about just nx times cx plus ny times cy, right? The problem here is that the normal in this case is, as its name would imply, is normal. It's a normalized value. What that means is this is true, right? This is the equation that tells you something is a normal. The vector Euclidean length of that normal is equal to 1. That's why it's normal, right? But the problem is, if you look at that equation, that's not the same equation that we would want for blending. For blending, right, this is normal. It is also another way of saying 2 norm. Okay? Now, I don't know that we ever talked about norms before. But what norms are there's a set of ways you can talk about normalized values. This is just one of them. The Euclidean 2 norm in this case is when you square and then square root, right? So square the components, sum them together, square root them. That's a 2 norm. But there is also a 1 norm. By the way, there's also an infinity norm. I think I've mentioned these on Handmade Hero before. That's when you raise everything to the infinity and then infinite root them. And that just has the effect of picking out the maximum value, right? So this is just what's the max, right? Well, the 1 norm is exactly the same as the 2 norm, is exactly the same as the infinity norm. You're just playing with the power. So the 1 norm is the non-root, I don't know if that's a thing you can write, but of everything raised to just 1 power, right? So it's effectively nx plus ny equals 1. That's the 1 norm. Now, why did I bring any of this up? Am I just going off on one of these tangents? Well, no, we actually care. The reason we care about the 1 norm is the 1 norm is the thing that produces a linear blend, right? If the blend weights sum to 1, then we have properly linearly blended our values together. If the square of the values square rooted sums to 1, well, this is not the same, right? This equation is not true. These are not the same. For any number of reasons, even just the most basic observation can show you that if you had a negative here, it would have gotten erased immediately by the square, right? So clearly, these aren't even the same, even with respect to sign, but they're not going to be the same with respect to quantity either, because although a value squared square rooted will only lose its sign, right? But otherwise, the magnitude is the same. Once you add two things together, a squared plus b squared square rooted is not the same as a plus b, right? It doesn't, the square root does not distribute across terms like that, across additive terms. It's non-distributive. So because this is not true, we can't really use nx plus ny because the values will be wrong. We want them to look like this, but instead they will look like that, and we will end up over adding. We'll end up with brighter light than we should have added when we're adding those light values together, right? What can we do? What can we do? Are we just screwed? Is that it? Is that the end of the ballgame? Well, no. Fortunately, if you look at what has to happen here, if I want to enforce this equation, right? If this is something that's true, I want to be true. I want to be true. Well, it's just math, right? How would I make it true? Well, what I know right now is I want nx, like effectively what I'm saying is I want like an nx prime plus an ny prime. I want those to equal 1, right? But what I've got right now is I've got an nx regular plus an ny regular that equals some other thing, right? And in fact, whatever that other thing is, I don't really care. Let's just say it equals some random value. It just equals a, right? Who cares what it is? So if I know I have this, right, but I want to have this, how can I get somewhere with that, right? Well, it's pretty easy to produce this equation out of this equation, actually, right? Because if you look at what's happening on this side, the only difference between these two equations is the a, right? If I just divide these by a, right? If I just divide by a, I actually get this equation here, right? So I don't even have to really do the math and solve for anything. I can just see that actually dividing by a produces the correct result, right? So since I have a normal, right, and I know that I can add the values and I will always get a non-zero answer, right? Because they can't be negative, it's a normal. You know what I'm saying? I can just absolute value them if I want to, right? I can just say that if I want to, right? I can just enforce them to be positive. I know they always have a reasonable magnitude. They can't both be 0. One could be 0, but the other can't, right? So when I add these together, I know, and I guess I should say this. When I add these together, if I just don't let them be negative, if I use their absolute value, I would get a value that, if divided, would give me valid sum to 1, right? That produces a clean linear blend for me. So if I want to, I actually can, in here, do something like, all right, let's force this to be linear blendable. Let's find a way to get a UVW out of this n, right? And so what I can do there is say, all right, step 1 is just to say, let me produce an absolute value for each of these. And I think we have... yeah. So let's first take the absolute value of each of these parameters, right? And we'll talk a little bit about what we need to do with the sign later, because we will actually use that sign. We just don't need it for blending, right? So we'd want to produce the absolute value here. And then what we'd want to do is make sure that our UVW is divided by so basically some kind of like inverse norm here, we want to produce that inverse a value. So we want to produce 1 over a here. And what did I say a was? Well, it's just the sum of all the values. Right? It's the 1 norm. So once we produce that inversion, we're pretty much good to go. We've got the blend values we actually want. And so then the only question is, well, what do we actually blend together? Well, obviously we need to know with our light probe. Nope. Here we go. With our light probe here, obviously we need to know which of these 6 corresponds to the things that we're going to blend together. But as you can imagine, if we're sampling out of a cube, right? So the idea here is that we've got some cube, right? And each of the faces has some lighting information on it, right? Then what we can effectively imagine is almost like a star pattern, right? Here's my Z, my Y, positive, X, right? And I've got a sample at each of those locations. So I've got a sample at negative and positive, right? Each one of those. And so what I want to do here is I want to produce whatever the colors are that I should blend between. I want to first select a positive or negative based on the sign of what the normal was before I absolute valued it, right? So that's why I was saying this absolute value, we're going to use the sign. We're just not using it yet. So we want to know the sign, and we're going to produce one value for each of these, but once we produce the value, then we're good to go from there, right? So all we really need to do is say, all right, we're going to produce, and you know, wherever the normal is, let's say the normal's pointing out that direction or something, right? We know we're just going to collect, okay, it's pointing down like negative y, so we're going to grab the negative y one. It's positive z, so we're going to grab the positive z color, and negative x. So we're going to grab those 3 colors, and then we'll do our blend with just 3 things, using the UVW that we actually have, right? So in here, we can just say, all right, let's do that. The result is just our UVWX times our X color, our UVWY times our Y color, and our UVWZ times our Z color, right? And that's the result. And the key here is we just need to pick these colors. So our X color is something, our Y color is something, and our Z color is something. And the question is, what is it, right? And so here we have our color table. I believe, here we go. We already had a convention, and we should stick to it so that everything in the game uses the same convention. You can see what they were here. It was like negative y, positive x, negative x for the axes. Oh, sorry. This is the direction. So we actually want to use this part of it. These are the axes you would impose on there. So this is x positive. I'm sorry, x negative. This is x positive, right? And so in here, we would pick one of either color, you know, x negative, x positive. So we kind of do like if, you know, nx less than 0, and the same would be true for each of these. You can see it just goes up the axis set. And so that would get us all of our colors that we need here. And then we're done. So that lets us pick, oh, well, if we don't have a typo, we're done. So that lets us pick which of our colors we're going to blend between, and then we blend between them to get the final result based on where the normal was pointing. So that's a way of collapsing down 6 samples into one based on a normal that can like smoothly vary around them, right? Now, there's ways we can probably make this better than it is, right? This, like the way these are happening here, you could imagine us doing an actual 6-way blend, which might actually be faster, by just using a clamp right? So you would do like this can be made. I'll just put the to do in. There's a lot we can do to just make this not have any branches in it or anything like that. Absolute value obviously doesn't require any branching either. It just knocks out the sign bit. So we can knock out the sign bit, do the blend, and we'll just use min and max to threshold our values. And I think we can make this just a thing that's like a bunch of adds, right? It's just a 6-way MAD that, you know, it's not nothing. There's a lot of, because each color, you know, there's a lot of values there. So it's a fair number of floppies. But it's not going to be really all that much. And so this makes it look worse than it is. We can do a much more straightforward thing here that doesn't require like a conditional move or something like this does. We can just use a select there, in fact. Would be another way to do it, right? So we could do 3 ops to build the color values and then do the combine or something like that. So there's a lot of things we can do here. This is not an ugly routine. It can be made quite clean and simple, I think. But I don't want to do that optimization until we get everything going so that we can see how we want to slot in, because maybe we'll end up we might be doing 4 of these at a time for all I know. Who knows what we're going to end up doing. So I think we kind of want to wait a little bit on that before we get to fancy. So looking at the rest of this now, you can see we've got a few functions we need to sort of implement here, and I'll go ahead and do that. So here's my accumulate probe function I got to do. That's going to take a light probe. We'll call that A for accumulator. Then we're going to have the T value that we're actually going to use, or maybe we'll call it the C value for coefficient because there's only one of them. And it's not a lerp, it's actually just a accumulation. And then we have a P0 value there. That P0 value is the light probe that's the source. And so here what we want to do is, again, we're just sort of doing a color summation here. So what we want to do is for every one of these, we want to effectively just add the corresponding value in the light probe in question. Oops. Right? So it's literally just a distribution of this. I only even wrote this function. Oops. Just so I wouldn't have to type that many times, but it's literally just a distribution of the sum. So these would just get inlined, and this would just be happening directly, right? So again, very, very, very simple. Just producing a summation there, nothing fancy. So I think that's almost everything, and then we have our kind of lighting stuff more or less solved, I think, and we can move on to the next phase, which is trying to integrate it in, which we'll probably have to wait till tomorrow to do. But if you take a look at what we still have remaining, the only thing we did not do is fussing with the grid. So all of the grid, you can see here, all of the grid functions are currently stubbed, and there's nothing there to implement them. So you can see that we've got a bunch of things for that. Let's go ahead and lay out what they are. Oops. So assuming we have a spatial index, one of the things we want to do is produce the center of a particular cell. That's one thing we want to be able to do. Another thing we want to be able to do is get back the slot. This is what's actually stored in the spatial index, which is just that, you know, really simple 16-bit integer that tells you which light probe in the set of light probes we're talking about. And so final thing is map it to grid, and this one's going to be the harder one. This one's going to have, because we have to return the UVWs potentially as well. I don't know exactly how we're going to work that out. We'll have to think about it a little bit. Anyway, so in this case, for get center of, for the spatial index, we know that we've got a min corner somewhere, right? We're going to have that. In fact, it's already written in there, right? I'm going to store the cell dim, because why not? So if we do the min corner plus the cell chord times the cell dim, right? That gives us the corner of the cell in question. And we just need to move half a grid cell further, right? That's all we actually need to do there. I'm trying to... I think that's what we want. Anyway, it doesn't really matter. I was trying to think of, is this the best way to organize the grid? But, you know, that will become clear in time if we need to make adjustments. Anyway, when we're doing get center of here, what I want to be able to do now is say, all right, I need you to get, this is the min corner. And in fact, you know, we could just duplicate this routine. If we want to get the actual center, all we would need to do here is add half an index, right, when we do our multiply. So that's pretty straightforward. Now, in both cases, we need a way of converting a V3U to a V3. That's fine. We'll have that. And then I think, you know, once we implement once we implement those V3Us, which we kind of already have implemented, and we're just going to move them into the math library. They were called Gen V3s before, but we're going to implement them as a V3U. That should all be fine. And then so finally, when we go to get corner line index, in this case, now we just need ways of looking up into the spatial index. For now, I'm going to stick with assertions, but I don't know if we want to use clamping in the future. It may be best to use clamping. Again, because that's pretty cheap. In SSE, it's not very hard to do clamping, so sometimes you just do it instead. So it's hard to say exactly how we want to do that. But either way, we know that to get our light index, what we want to do here is take that array that stores all the information in the voxel, and we want to move by the cell chords somehow, right? So we're going to be doing something like this. And so to look at how these would get added in there, I intentionally sort of said there's a dim power of 2 here, which means the light probe spatial index is not going to really be allowed to be an arbitrary number. You always have to have the sides be a power of 2. And the reason I want to do that is because it just makes indexing easier. It means that instead of having to do any of this stuff, we can literally just build a composite index value, sort of something like this. What do I want to call this? Get something like that. I don't know. But basically, if you give it some cell coordinates, what we want to be able to do is just produce an index out of those. And we can produce that literally by just bit manipulation. So the Z would get shifted up by something. The Y would get shifted up by something. And the X would not. It would just get OR'd in there, right? And we do need, in this case, a spatial index bit here. But after that, we're good to go. So here we would just say, all right, the dim pow 2 here, dim pow 2 here. And so we know that, let's say that the dimension power of 2, you know, what's that going to be? Let's say the dimension power of 2 is, you know, 5, 8, Who knows? That means there's 256 values x could take on, right? So we just need to shift up by 8 to make sure y doesn't interfere with that. Done. And then when we get to z, we need to shift up by that twice, right? So it's really just saying shift it up by that 2 times, right? What's amusing about that is that's just a double shift, right? If you want to do, oops, it that way, you can. I'll let that be the compiler's discretion. I don't really care how it wants to do it. Depends on what kind of code it's going to generate there. But point being, we just want to shift up by twice that, again, for the z value. That will produce a composite index, and then we return the index, and we're done, right? Easy peasy lemon squeezy. So if we want to make sure that these things are always inside the bounds when we actually look them up, then there also, we kind of have to, excuse me, take some care. For now, I'm just going to say, whatevs, let's just, take them and we'll start to deal with out-of-boundsness later on, right? One way we could do that too is just say, look here, let me do this. Let's get that index in play, like so. What I can do here is say, look, let's put an assertion in. We know that the index has to be less than the dim pow2. Multiplied out, right? So if we take the dim pow2 and we say, we know that each one of the signs of this is going to effectively be like raised to that power 2, right? Like if it was 0, it's one dimension. It's 1. If it was 2, it's 2. If it's 3, it's 4. If it's 4, it's 16, and so on, right? So we know that this is one. I'm trying to explain this, but my brain is having a hard time coming up with the words, so I'm just going to draw it for you. We know that if we want to produce 2 to the n, right, that 1 shifted up by n gives us that value, right? So when we say dim power of 2, that's just an n, right? That's just this. So anytime we want to know how many are on one of our voxel sides, it's just 2 to the n, which is just 1 shifted up by n, right? Now, if we want to know how many there are total in the voxel, we know that we would just multiply the number of ones along x times the number of ones along y times the number of ones along z, right? Which is 2 to the n times 2 to the n times 2 to the n. Now, we know that if you are going to add 2 to the n's together, if you're going to multiply 2 to the n's together, you're just going to add the n's, right? Because multiplication is just adding more powers. So it's really just n plus n plus n, right? It's 2 to the n plus n plus n. That means if we wanted to do the shift, we're really just talking about 1 shifted up by n plus n plus n, right? But we don't really need to do n plus n plus n because that's just 3n, right? So really, we just want that. And so 1 shifted up by 3n is actually going to give us the total number of things that can be in our voxel. I didn't know how to say that without having things to point to, so sorry. Anyway, so when we do this, all we need to do to figure out how many there are total, that's how many there are along 1. All we need to do to figure out how many there are along all are that. And if they were different, we could just, instead of 3 times, we could just do plus there, right? So we could do dimpow2.x plus dimpow2.y times dimpow2 times z or something, right? So we can actually be flexible there if we want to. So, we could play around with that if we find that it's like too discrete in z or whatever. I don't know, right? So just, keep that in mind that this doesn't really get particularly more complicated. at all if we want them to be different spatial dimensions for each one. In fact, maybe we should just write it that way now. I don't know. You know, you can, like, if we were to do that, it would literally just be this. Right? I don't think there's anything else we would have to do. And the same is true for this. You would just say, well, there's the Z, there's the Y, and I need to account for this Y shift in here, right? Oh, sorry. My bad. Right? Because I almost put Y there. You don't want to shift up Y by Y's power of 2 because you're making room for X in the bottom bits. So what you're doing is shifting up by however many X needed to use, right? Then when we come up here, we want to shift by how many Y needed to use, but we need to have already been shifted by X, right? Now, since we're already doing this shift by X, we can, instead of doing 2 shifts there, we could also just do, well, why don't we just merge these 2 together first and then do the shift as a group, right? So if you look at doing it this way, that makes it a little cleaner potentially, right? So let's say we took, do we have that whole thing there? There we go. So here you can see, I take the Z coordinate, I shift that up by Y, I orient the Y component, I shift that up by X, I orient the X component. So that way it reduces the shifting. I only have to shift up once for each thing I merge in, and that could be possibly a little bit more fun. Who knows, right? All right, so I think that gets me everything I need, and now you can even set these things to arbitrary scales power 2. Because I don't know that it doesn't look like it's really any more expensive to do it one way or the other. It's not really an issue. So in here, once we do our get probe lighting for, we know we've got, and also we use it here in map into grid, we know we've got one more thing we've got to do, which is if we have an arbitrary position, we have to have some way of producing the actual, we have to have some way of actually producing from an arbitrary 3D point what the coordinates of the grid are, which are like a discrete thing, right? And we've done this so many times on Handmade here, I'm not going to belabor the point, but it's trivial, right? For any given spatial index, we know we have the minimum corner. So first we just make the P relative to the minimum corner, right? That's the vector from the minimum corner of our spatial index to the point in question. After we do that, we know all we have to do is say, well, after we get that relative one, we know that each cell is exactly this large. So we can just say, let's take it and divide it effectively, right? Because multiplying by the inverse cell dimension is the same as dividing by the cell dimension. Again, that's an actual per element multiplication, so we got to invoke a Hadamard product there. I don't use vector product as multiply because who knows what that means. Do you want dot product? Do you want a Hadamard product? Do you want a vector cross product? There's all kinds of vector products out there. So I like to say which one I'm using. In this case, it's Hadamard product. That gets us back the coordinates in float. So this is basically our, our F chord. F chord. Probably didn't just hum an F chord because I don't have perfect pitch, but you know what I'm saying. Anyway, the F chord is still in floating point. So now what we want to do is be able to truncate that coordinate down. And in so doing, we will also be able to produce that UVW. That's the that's the reason why I was sort of suggesting that we probably want to produce both values here. But we'll get to that in a second. So if I want to now get my V3U out of it, I want to be able to do like a truncate on this F chord here, and that will produce my result. But once I have, that truncation, I can pretty easily produce the, with using this F chord, I can pretty easily produce the UVW, right? The UVW in this case is just the F chord minus whatever the truncated version was, right? So there's that. Who knows how we want to implement that. But point being, we would like to return this value as well, because a lot of people actually need it, as you can see here, and they don't have F-chord. You could just ask them to do this themselves outside, but they don't have the multiplied version. And they need that multiplied version because otherwise it's not the right scale, right, for those 0 to 1 values. So that raises the question of how do we want to return this back? Let's say we do this. I'm happy with it. There we go. Hopefully everyone else is too. And then when you call map into grid, if you only want one of the things, you just get one of the things. If you want both of the things, you take them. So here I can get my cell chord, but I can also get my UVW, right? So that seems fine. And when we do the map into grid here, we only really wanted the cell chord, so we can just pluck that out and skip the UVW entirely because we don't care what that UVW was anyway. And then I think we're pretty much good to go. I need the V3U to exist, and since we've already kind of implemented it, I'm going to just say now is probably the time to upgrade our Gen V3 into a real value because we want it. And you can see basically everyone needs it there. So let's go ahead and do that. Oops, I didn't mean to make a new buffer. So if we take a look at our gen math, you can see we've got this union Gen V3 here. I'm going to go ahead and type def a Gen V3 to a V3U because I want to now make this a first class citizen there. I know those are S32s, so I guess this is really a V3S. But I'm also fine with that. I don't really care if it's a U or an S in this case. So I think that'd be fine. We could do this, and then I'll use V3Ss in the rest of the stuff as well. I think there's a handmade types here where we actually define these guys, and so I'll follow suit there. And just say here we've got a V3S in the mix. And yeah, I'll just leave it at that for now. There's more we could do there, but I'm not going to bother for the time being. And then in the lighting stuff, I'll just say, all right, you know when I said V3U, I think pretty much everywhere we'll just use S instead. Sorry for the psych out, but that's just how it's going to be. And I don't think there's very much we have to do to fix that. Oh, and this probably should get moved out into here as well. There we go. Let's make that an incredibly long and ridiculous name. Go. And other than that, not a lot we have to do. So we're just going to have to implement that V3S. I think then we're good to go, right? Not a whole lot else to do there. This needs to exist. And that's an S. And that's it. So we now need to actually take that genmath.cpp and we're going to have to get yeah, we didn't really do much with it, as you can see here. So those are all part of those gen volumes, which are a different thing. So in the math world of things, I'm going to go ahead and start implementing some of these. So we've got our V3S here, and just want to make sure we actually have some operators that it can use. So we'll start with those, and then really mostly what we need is just ways of converting these things. So mostly what I need is, like, I want a truncate, oops, to v3s for v3. And I thought we had like a truncate. So you know what? Floor is fine. Floor is totally what I want anyway, effectively. So I'm fine with that. So in here, where we're doing this sort of floor function, we're just going to do that on each of its values, and that'll produce the floor that we wanted. So that's actually totally fine. Oops, that's actually totally fine. I think all those are fine too. No whirly worries there. So then the only other thing we, I think, needed, I can't quite remember, is the ability to change one of these V3S's back into a V3. That's just a simple load. That's not going to do anything interesting at all. Doesn't really even change the value. And that's it. All right, so let's start to clean things up here as we go. Looks like we wanted a shorthand there for creating one of these, which makes sense. Again, pretty simple. What else we need? Get probe from cell. So I think that's just this, right? So we do have a bit of an issue here that I think we kind of want to be aware of. But actually, I guess it's fine because there's already a 0. So we always want to return a value from this, but I realize that I guess we kind of can. Because if there's a 0, we just return the null 0 probe, which is just has nothing in it. So that's actually fine. So here we want to take this nonsense, right? And we want to do the indexing. So that's, in this case, just going to piggyback on top of this function, actually. So where we get the spatial index address and the corner line index, this stuff here, all we're doing is we're really just going to call that. And we're going to say, give us what would be whatever the index is in there. And we want to get that probe, right? And so this is really just a convenience function built out of things we already knew we needed. And in some cases already wrote. There's a signed, unsigned mismatch somewhere. Probably this. Yeah. And then finally, we need a way of actually getting one of these. And hey, I'm out of time, which is good because we just finished implementing everything. Tomorrow can be the day when we actually try to wire some of this stuff up. Oops. All right. Anything else we got? So cell dimension here was just a typo. We meant to get that off of the spatial index, so that's nothing big there. Here, this is just needs to get its new ridiculous long name. Here, where we've got that truncate, it's really just called floor. And then we finally have a get probe lighting for, which I don't remember what that actually took. I think it just needs that. Didn't have the solution, which it needs to look up the light probes. And then I think we're done. And you can see that, you know, there's no sense in running this at this point because it can't do anything. And the reason for that is we aren't actually submitting or generating light probes, right? And you can see that by the fact that where those light probes would be, they don't actually exist, right? So in other words, in here somewhere, there has to be something that actually stores the light probes. So right here, right, we would need that. And that produces a correctly compiling program, but that one that can't actually do anything because nobody will ever put any light probes in there, and so there's no reason to actually call these functions. But that is exactly what we can start doing tomorrow. I will go ahead and go to the brief Q&A now. Actually, it doesn't have to be brief, I suppose. It could just be a regular Q&A. Long Boolean. Concerning moving light probes, could you have special purpose light probes that only affect the lighting of certain things that move, so you would end up with things that move and things that don't, and most other probes in the lighting system would be unmoving, and perhaps the moving probes could use some of the unmoving information, and the unmoving could gradually sample from the moving. Yes, so I guess the main problem would be in the shader. So if you think about what's going to happen, in our shader, we're going to have to sample somehow. And in order to sample lighting for the world in general, like all the grass and all the walls and, you know, all the stuff that fills up most of the screen, that's going to want to sample from, you know, a common set of light probes that just interpolates between. So that's all good. But if you wanted to have accurate sampling of a moving object that had its own probe, what we could do is have a different sampler, a different pixel shader, that instead of sampling from 8 light probes and blending between them, it actually just sampled from one specific light probe that it had the index to, right? And then we would just assign certain objects to that shader, and they would do that, right? Now, I don't know that I actually care about that. So I don't think we will do that. But there's no reason you couldn't do it, right? And furthermore, they don't actually need to be involved in the system at all in any other way. They can just be a separate sideband of light indices that don't even contribute to the lighting solution. They could literally just be 10 moving light probes that you just stick to enemies in the hero, for more accurate lighting or something, and they just accumulate their results themselves, right? And you could totally do that. I don't know that we need to do that. I don't know that there's any real benefit to doing that, because I don't know that we need any kind of special accuracy in that way. But you could totally, there's no reason you couldn't do a system like that. It would be totally fine. When and how often do we plan to compute the light probes? Well, every frame they're updated. It's literally just the same lighting we're running right now. We're just going to change to running so right now our world geometry is also the collection geometry. The only change we're making is now our probes are going to be the collection geometry and the world is going to be the reflection geometry. And so we're just going to be exactly the way we're doing it now, where we have about, I think, 100 frame window of averaged out values. So it's once a second or so at 60 frames a second, maybe once every 2 seconds more like. The lighting has been completely changed, but it's very gradual so that you don't see too much flicker in terms of like lower sampling. And what that value is that we'll actually set it to eventually, I don't know. We'll have to see what happens, right? But we'll go from there. But it's continuously updated all the time. How are square roots computed and how fast are they? The answer depends on how accurate you want the square root to be. So it's pretty similar to division in that sense, but I'll show you. All right. So if you take a look, if you just put in square root to the Intel Intrinsics guide, this is a pretty good guide to how fast square root will be, just as a pure ballpark estimate on the CPU side. Remember, the GPU has its own separate speeds for all of the operations. So it depends. If you're talking about in a shader, you need to look up information on the particular GPU in question. But assuming you're talking about a CPU side, almost everything is x64 unless you're on a phone or something, which is ARM. And then you need to look up different tables for square root, right? But on here, what you end up with is when we look at the available square root operations, you can see there's quite a few different ones. Now, most people are not going to have AVX 512 yet, so we're not going to talk about things that are up in that range. Let's talk about just stuff that you know everybody who plays a game on a PC will have, right? So that's this. Now, soon, most people will also have this, right? And maybe even that. But at the moment, we're just talking about this. As you can see, like most of these are there. Once you get to this, it's you're out into huge numbers of intrinsics depending on where you're using masking and all this, how wide you're doing it and blah, blah, blah. But, point being, this is mostly where we're at. So if you take a look at these functions, there's two ways you can compute a square root, and they're not the same. So let's talk about just actually computing the square root first. So the packed single precision square root, this is for, so see that SS versus the PS there? So the difference between the SS and the PS is just whether it does 4 at a time, which is the squirt PS, or whether it does just 1, which is the squirt SS, right? Now, ignore Knight's Landing. Knight's Landing is a completely... It has nothing to do with gaming. That's a HPC part that's... it's a Larrabee core thing. It doesn't have any... just ignore that. So we're looking at, Skylake, or if that's what the modern chips all are, or one of these other ones down here if you're looking at more compatibility with older machines. So mostly you're looking at a Skylake core, and what you can see on a Skylake core, if you're doing a square root of either 4 or just 1 value, is you can expect to pay 13 cycles from start to end. So when you issue the square root, it will take 13 processor cycles to get the answer back. But you can ask for one every 3 cycles. So if you start a square root, you can actually ask for another one 3 cycles later, and another one 3 cycles after that, and another one 3 cycles after that. So in terms of the pipelining, you can actually potentially get a lot more than one done every 13 cycles. You can actually get one done every 3 cycles if you have a bunch of them to do, right? So that's probably the more useful number to look at, which is to say that in a long dependency chain where you're pushing a huge set of sequential operations through, and that's all you have to do, then it's 13 cycles. But if you have lots of things to do on multiple things at once, you can get some pipelining there, you're going to pay closer to just the 3, right? So usually in heterogeneous computing, where you got a lot of stuff going on, you can look at this number as being closer to what you'll actually receive than this number, which is more of the worst possible case when you don't have anything else you can be doing with the chip. So that's basically the idea, right? And you can see that modern Skylake cores can do 4 of these at once as well, with no penalty. So that's pretty cool. Now, that's the most expensive way to do it. I mean, unless you want to do double precision, which we don't, right? So there you go. If you want something cheaper, you actually have an option, and that is the reciprocal square root. So the reciprocal square root doesn't produce the square root, it produces 1 over the square root, which is like a square root and a divide together, right? Why is that an instruction? Well, it's because normally what you do after you square root something is you divide by it, right? It's a normalization. It's usually what you're doing. So they do both of those together. So you're actually saving the divide and the square root, doing it in one, right? And when you do this, the only caveat, you can see how fast it is. It's latency 4, but it's throughput 1. You can issue 1 every cycle, right? But what you can see here is that reciprocal square root, it doesn't quite give you the right answer, right? So the error is, proportional to this value here, which is what, half the bits are wrong, something like that. Up to half the bits could be wrong. I'm just thinking there's a 24-bit mantissa and a floating point value, so 1.5 times 2 to the 12th, negative 12th is like half the bits, I guess. It's 1.5, so it's a little more than half the bits. Maybe it's 13 of the 24 bits. I don't know. So I'm not really sure how to read that. I'm not a floating point accuracy kind of guy. Otherwise, I would have a very strong statement about what that was. I'm not. The point being, if you just need it to be in the ballpark, like I'm trying to normalize this thing more or less, then actually you can do it even faster, right? So rather than waiting 3 cycles to issue the next one, you can issue it every cycle. You can issue a new one. And they still take 4 to come back, but hey, that's better than 13, right, as well. So even if you have to wait for the result, it's okay. So in the old days, a square root used to be awful. You really didn't want to do it. And in fact, we did all kinds of hacks to not do it. Nowadays, a square root is kind of free. Like, it's not free, but it's really low on the set of things you're worried about, whereas before it used to be really high on the set of things you were worried about. And so there was definitely a mental shift there when CPUs started getting fast reciprocal square root, because you can and they now have fast regular square root too, right? So you've got both of those things at your disposal, and if you want to, you can also, most of these routines that give you approximate results, they're set up to also allow you to refine the results. So if you needed a better answer than this, you could usually do a Newton-Raphson style refinement step if you want, right? And again, this all just depends. But whether that's faster than just doing the correct thing now that it's there, hard to say, right? Is CRT dependency a Visual Studio feature only, or do other compilers such as GCC and Clang have it too? Also, does the dependency include C++ or just C? Actually, it's arguably even worse in GCC and LLVM, but it really depends on what you're doing. What I would say is that compilers in general have a very bad habit of relying on their runtime library to produce code. I personally think that if a compiler, if you do not pound include anything in your C program at all, a compiler should produce 0 dependencies. That is not what happens. Compilers actually produce a ton of dependencies to their own CRT. Stack probe calls, memset calls, memcopy calls, stack frame checking, C++ static initializer walking. It's awful. In my opinion, that should be completely unacceptable. Like you should be absolutely not allowed to release a C compiler or a C++ compiler that with no includes and no libs, when you just compile a program, somehow it produces a dependency. That should be completely off the table. Sadly, it's not. So what you will see is that a lot of compilers, both Visual Studio, GCC, and Clang, all of them, insert a ton of garbage into the compiled code that you then have to produce your own implementation for if you want to link without their runtime library. I wish that was just considered completely unacceptable. Like you wouldn't be able to even pass a single benchmark, compiler benchmark, if you did that. Sadly, it's not. And so we're stuck with it. I didn't really see this pop up before. Do you think using Direct 2D for a 2D game is a good idea if I want to implement it from scratch, or would you rather use DX1112 today? So, is Direct 2D, I don't even know, is that still around? I didn't even realize that was still around, but maybe it is. I wouldn't go anywhere near Direct 2D. It's a complete pile of garbage. I would definitely just use DX11. You probably went over this last week, but how do you plan to make this faster than what we had before? There's actually 2 ways it'll be much faster. One, we can use many fewer sample points, which is critical. And 2, we can compute those sample points faster because we don't have to do stuff like looking at when something hits a face, which sample point it's using. So our raycasting can speed up dramatically as well. So I think we'll be able to do better. Now, it may not be the case that it may not get that much faster on the raycasting side because of the expensive voxel lookup, but we'll see. Hey, I love the trick with the hot loading, but having a hard time grasping the general idea. Could you make a kind of generic overlooking explanation? I mean, I explained it and implemented it in like one video, so I'm not sure how I would make something more straightforward than that. I mean, it's literally like one video where I like explain it and implemented it, right? So I'm not really sure what I could do to be more clear than that. And as for whether it works with third-party libraries, I mean, that would completely depend on the third-party library, right? again, in that way that I find most people's modern way of programming to be very bad, I would consider it a bare minimum that any library you ship should, of course, work with hot loading. I mean, that should just be a given. Because as long as that library is memory conscious and allows the user to pass in the memory it wants it to use, it will just work with hot loading. But of course, most modern libraries are written to just anything goes. Let's call malloc everywhere, and who knows where the memory came from or where it's going. And at that point, yeah, sure, you lose hot loading. You gain a bunch of fragmentation problems. It's just, yeah, modern code that you find on the internet usually sucks. And once in a while it's not bad, but usually it's terrible. So the answer to normally, does X, where X is a good programming thing, work with Y, where Y is a commonly available third-party library? The answer is usually no, because Y was usually written poorly. Whether SFML is in that category or not, I don't know, because I've never looked at it. And by the way, the reason I said DX11 and not DX12 is because DX12 is not very widely supported. Unless they've changed things recently, if you ship on DX12, you can only run on Windows 10. So that's it. You really can't use it unless you don't want to target Windows 7 and Windows 8, which, you know, is like 40% of the existing market, I think. So, you know, DX12 is a ways away, I think, in terms of being something you could cleanly target for I mean, because you're talking about a 2D game, right? You know, if you're talking about the latest game from, you know, Mr. Renderland or whatever, where it's like requires the latest possible machine, then maybe requiring Windows 10 doesn't matter, because you figure you know that everyone has a really new machine, right? But you know, that's just not, it's just not feasible for a 2D. A 2D game wants to be able to run, when it comes to ship time, you want to be able to like turn off features and turn off stuff and have it run on pretty low end stuff, right? Like, why wouldn't you? Because it's 2D. It shouldn't require the latest possible system, you know? I guess that's what I'd say. So yeah, so I don't think Direct3D 12 is really a viable thing to ship a game on right now, unless you're really, really pushing people to adopt the very latest of everything. And a 2D game really shouldn't probably be doing that, I guess how I'd say it. In 5 years or so, I expect that number will start to drop pretty well. So, you know, you might be at a case where 90% of the game community that you might be targeting, market out there, those are probably going to be running Windows 10, you know? And at that point, it's probably fair to say, look, I don't care about the other 5% of the market or something, or 10% of the market. I can live on 90% just fine. And plus, how many games do people with machines that old really buy anyway, you know? So at some point, it becomes fine. Much like that same thing was true of DirectX 11, right? At one point, it was tied completely to, you know, Windows 7 or something. And so you'd be like, well, there's a lot of machines running Windows XP, so I'm not going to do it, or whatever. But eventually, everyone finally begrudgingly moves up to Microsoft's latest and worst operating system. And then, you know, you can use the next revision up, and so on. Do you have an opinion on C callbacks and void star user data? Do you know any alternatives? Do you have an opinion on GCC's nested functions? I am fine with C callbacks and void star user data. I like them. And I would say there are plenty of alternatives, but none of them are as good. GCC's nested functions aren't something that I've really used myself. So, you know, I probably wouldn't say anything definitive one way or the other. I'm pretty early on in the stream. My sound was scratchy. Do you end up making a separate thread? So we aren't really super concerned with sound. When we go to actually finish off everything and want to start doing testing on machines and stuff, we will probably do some changes to the sound. But they probably wouldn't involve replacing D-sound. For example, I have a Windows 10 machine at work. The only thing that works correctly on it is direct sound. Wasapi fails. WDM fails. In high-end audio software, this is Reaper, right? Which is very good at audio. Only direct sound works, right? So I think shipping on something that doesn't work on direct sound is probably a big mistake, because almost nothing ever seems to work on Windows sound-wise. They introduce, they take a page from the Linux playbook. They introduced 7 different APIs for sound mixing. Doesn't make any sense. There's no reason to do that, but they did it, and most of them don't work. They randomly work, they randomly don't. I don't know how you get in that situation, but they do. And so, you know, D-sound and wave out are like the 2 things you can count on that seem to always work. Everything else may just fail. I'm not talking about sounding bad, I'm talking about just fail. And who knows why? I think it has to do with whether it's the native, whether it's like a modern Realtek chip, or if like you plug in a USB external sound thing or something, then suddenly it only has direct sound emulation or something. I don't know. And threading usually has nothing to do with updating the sound. If you need to just add some look ahead, some more padding to your sound, then you won't get skipping, right? About hot loading game code, is it a common thing between game programmers? I would say yes. I feel like most games need some kind of hot loading. So usually games take one of 2 tacks. Either they hot load real code, or they interpret script code so that, you know, that's still hot loading, right? It's just not compiled. But you usually have one or the other, because the turnaround time is too slow otherwise for some of the things you want to do. And turnaround time can get worse too, and in certain game engines take forever to build and start up and stuff like that. So at that point you really, really need ways to build tiny parts of them and reload them in. You could argue that's because the rest of the engine's architecture is bad, but hey, you know, Unity and Unreal are both giant pigs. So, you know, if you're using engines like you really need a way to interpret or hot load code in those, so you can't be restarting everything every time. It's not feasible. Stretch DI bits has started failing after changing the resolution to 960 by 540. So stretch DI bits is not going to fail unless something failed earlier on to get appropriate surfaces. So I don't think that's what's probably failing. I think you're probably seeing a failure somewhere else. Would you recommend any free Windows debuggers? No, I would not. However, I would recommend going to remedy.itch.io and paying $20 for this one. I guess I would say if you cannot afford $20 for a debugger, I guess I would ask, how did you afford a computer? Since they're very expensive. Maybe it was gifted to you. In which case, maybe ask whoever that is to gift you a Remedy BG license, because at $20 it's pretty darn cheap. And it's been moving along really, really well. So that's what I would recommend. There's still some features that haven't been added to Remedy BG yet, so it's not quite as full featured as Dev Studio is, but it's way better than Dev Studio now in terms of like ease of use. It's much, much faster, starts up much, much more quickly, and refreshes infinitely faster. So it's just more pleasant to use. And at the rate that development on it's been going, I would say that I doubt it's going to be like 5 years before it catches up in terms of features to Visual Studio, because Visual Studio doesn't have that many debugging features. So I guess I would say it's probably going to catch up sooner than that. Really, the thing that's missing right now is just like breakpoint support and mini dumps. I guess those are the two things. It doesn't support mini dumps. It doesn't support like advanced breakpoints, like data and conditional breakpoints. I'm trying to think of other things Visual Studio can do that it can't do, but I can't. I mean, I think that's it, really. So it's close. And I don't know. I mean, George is on the chat right now. It's X13 Pixels. I don't know what his plans are. Like, I don't know when he's going to try to go for feature parity there, but those things do take a little bit of work to implement, but compared to what he's already gotten done, they're not that big, so I wouldn't be surprised to see those things come online sooner rather than later, actually. I mean, just based on how much has gotten done in the past 6 months or so. Have you ever used telemetry debugger? If you're talking about RAD's telemetry, it's not a debugger. It's a performance analyzer. Unless you're talking about, maybe you're talking about some other telemetry. I don't know. What do you tell me? Give me a link to what you're talking about. When I look for ways of looking up the position of objects in a game, e.g. for raycasting, some sort of graph or tree is always presented as essential. Are there other ways of doing such lookups efficiently? It seems like an array sorted by distance from the origin and doing lookups in ranges. So I guess what I would say is you're always going to have some kind of spatial partition, but the type of spatial partition is very widely varying. And so the thing that you suggested, which is an array sorted by the distance from the origin, would be totally valid. That's just a spatial partition where the partitioning is a binary partition split in rings around the origin. It's a binary tree, right, of splits where the split is a sphere centered at the origin with a particular radius, right? I don't know. I don't know really how to add anything else to it. Oh, wow. I was just looking at the chat. George says data breakpoints just got finished up today. Really? That's pretty huge. Because like I was just saying, like the only things you can really point to, I mean, someone else correct me if I'm wrong, because, you know, I don't know everything about Visual Studio Debugger, but the only things I could really think of that you couldn't do in Remedy that you could do in Visual Studio was like breakpoint stuff. And so if data breakpoints are in there, then that really means conditional breakpoints are the only thing that aren't in there yet. But that'd be about it. So it's getting close. L space YL. How do you run the bat compile on other platforms? I don't. I just have a build for every platform. So I have like a .bat and a .sh and so on. Fred the sequel says, the other thing you can do in Visual Studio is have your debugger not work properly. Correct. You can also have it be very slow. And George hasn't implemented that either, so thankfully. About mipmap generation, I was wondering why you decided to compute on CPU and not GPU. In addition, why did you decide to go with a simple box filter and not something smoother like a tent filter? So there's a lot you could say about that. Let me start with the second point first. The reason I tend to use a box filter when computing mipmaps is because it means you don't have to turn on trilinear filtering. And that's really it. Because the GPU, when it subsamples the mipmap, it's doing a box filter. So if you don't do a box filter, then your result of decimating the mipmap, of decimating the texels by 2, won't agree with the GPU's decimation by 2, and you might get some popping there, right? So if you choose to turn on some kind of other filter, you have to decide what your solution to that problem is going to be. Is it that it's just not going to be noticeable enough? Whatever. But I would be worried about popping, right? And another way to say it is that if it didn't pop, then it must be close enough to a box filter to not have been worth it, right? I don't know. Does that make sense? As far as why I did it on the CPU and not the GPU, just because there wasn't really a lot of reason to move it to the GPU. Everything we move to the GPU takes time away from the GPU, which we need for rendering. Since we have threads sitting around not really doing anything during load, it seems like they might as well generate the mipmaps. All right, I'm gonna kind of wrap it up. All right. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow on the series at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along with it at home. That's it for today. I will be back here tomorrow. It'll be early tomorrow. I have something scheduled in the afternoon, so I have to do Handmade Hero a little earlier. It'll be 10 to 12 instead of 12 to 1. Sorry, 12 to 2. So it's a little earlier tomorrow. That may make a difference for some people, just giving you the heads up. As always, on the watch page when we're not streaming, it's got the schedule, so you can head over there if you're curious about it. That's about it for today. I will start trying to integrate our lighting system into the game tomorrow, and then we can start to move the computation over to the probes. So again, it's a gradual process. It'll take us a few weekends to do, but then I think we'll be in good shape. Because I think we can both get a speed improvement there, and it solves our problem of how do we sample all the rest of our stuff in the game. So how do we light our grass and our entities and stuff, which we need to do as well. So I think that's what we want. I think it'll be good, but it'll just take us a bit to get there. So a couple weeks, and we'll do it. That's it. Thanks for joining me. Till tomorrow, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.